Okay, I'm going to start a few minutes early, but I'm going to do a mic check here. Okay, I'm trying to get the system up here. Once I know that there is. All right, I know there's audio. Okay, I want to address something that's incredibly annoying to me and give some justification, possible justification towards this assumption. Okay, first of all, he has this single journal bearing. The picture he shows is relatively thick crossed here. Yes, I believe in the structure he has that those are supported. However, let me give a justification as to the possibility that they may not be supported. If you look on a thin bearing, let's assume we have a thin bearing in which we have a seat here. I'm not a great artist, so I'm going to do the best I can. And let's say there's some ball bearings that sit in here. And essentially, these are seated to the ground. And essentially, let me try to do this from a side view. Okay. Here's the shaft opening. Here's the shoulder of the shaft. Here is a ball bearing sitting in there. And there, in fact, there's several ball bearings sitting in there. And the shoulder goes all the way around, in which it floats. Maybe it's best to, since I'm not a great artist, let me see if I can break out a okay. 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 So, for example, this might be a ball bearing here. Um, just pick that one. I don't know. Accept whatever it is. So there's your ball bearing. The shaft goes through and is fitted here, and the ball bearing sits down there. I don't need. So there's some CAD downloads, some things like that. $8, not a bad price. The key is, it is possible in some of these, given the tolerance, that the bearing seat could rotate freely to a degree. In other words, if I were to put a torque on here, what would the torque versus the resistance be? In other words, let me put it to you like this, more like we're moving an angle. And here's your torque versus the angle. Of course, 0 and 0, you actually could move this thing a while before your torque increased. So in other words, it's possible that there's enough free play in here, and if it's a free play here, there'd be enough free play so that this bearing could rotate back and forth in there and not supply a moment. Now, that's the only physical reason that I could see that he would allow this. Note, the couple moments are generally not applied if the body is supported elsewhere. See the examples. Okay, to me, that is very annoying to me. Because you don't tell somebody one thing, put exceptions on it without giving justification as to just why I'm dropping that or why I would drop that. So this is the only reason I could think of, is that this is the case. Now, most people who have taken apart an automobile in some form or other have come against the concept of tapered bearings. Let me see if I could find. I think I misspelled it. Tapered bearings. Okay, tapered bearings are kind of interesting. Okay, here's one of them. This is looks like this company has a lot, so let's just go there. So let's look at this. Here's a tapered bearing. Obviously, this is the internal thing. These are little tiny little cylinders that are tapered in there. Let's see. So I'm going to try to draw that on the drawing. And in other words, maybe you'd have a seat that sat right here. Here's your little rotating part. So I don't know how to do this, except these are the little rollers. Then you would have the internal seat, and you'd have the equivalent opposite the other way. So these little tapered rollers go around the whole way. Now, let's say you put a shaft in there, and I wouldn't suggest welding it, but you could shrink it so that these two are joined right here. If you push this shaft to the right, it's simply going to remove this and the rollers will fall out. In other words, if you look at this, you can just see this little cap right here could come right off, and you could take this little outer cap here and just set right on there. So what do they do in cars? They do something interesting. Okay, I'm again not a great artist, so I'm trying to do the best I can. Take another one, set it right here. Oh, geez. So this is kind of attached to the shaft. You have your rollers in here, and here's your little roller. That's an awful drawing of a roller. And there's your seat. So if you push this shaft this time, it takes this end and shoves it against the roller, and it's offset by that. In other words, this is attached to the ground somehow. So, sort of like that. You push the shaft the other way, it takes this roller, push that seat against these rollers. So what you do is you put enough pre-tension on this so there's no play left or right here. Okay, in this particular situation, this thing can take a moment exactly like that. There is no exception for this. You cannot make this assumption. That is not possible here. It makes perfect sense because if this is your automobile and here is your wheel and you put, 4,000 pounds here, you really don't want this thing to be able to rotate off like that. You don't want to be driving down the road with your car coming straight at you with your wheels like this. This is not the type of automobile you want. Here's your automobile. Here you are driving down it, thinking to yourself, oh my gosh, No, you don't want that. What you want is you want your wheels to sit like this. There's some bearing here on some type of axle in which the moment is completely resisted in this way. So yes, there is a moment. Yes, there is one. Justification is if you had one single bearing, then that's okay. Unfortunately, I gave one problem like this, and I regret doing it. I think his general assumption here is kind of incorrect, but I can't uh, speak for the author. um, okay, so let me get this out of the way. And here we go. So let's start looking at each of these problems. Okay, there are 3 problems in the homework, one of which is the annoyance, but let's just start here with this one. If you want to do a free body diagram, the free body diagram would look, hang on, let's see, mode, freeformed, and get a new, and what I would do, and I thought I was doing the selection there. New. Okay. I think I goofed that up. Okay. Okay, so there is removing of your supports. It became larger for some reason, so I shall shrink it some. Okay, so these are both pinned, so they both can take an X and a Y load. I'm going to move it to the right a little bit. Okay, I don't know what's going on. All right, here we go. All right, so I can take an AX. I'm assuming that was an A. Yeah. I can take an AY. Now, I can do the same thing here, but this is pinned, and this is pinned. So in fact, the only load that can occur would be a load along the axis of the object being this rod. So you could call it just D. I think it was called D. And that can be broken into a dx as well as a dy. Okay. Turns out this is 1.5. That's 1.5. So that angle, 45 degrees. So this means dx is nothing more than d over square root of 2. And this is nothing more than d over square root of 2. So in fact, you have 1, you have 2, and you have 3 unknowns, and only 3 unknowns. Luckily, you have some of the forces in the x, some of the forces in the y, and some of the moments. So you have 3 equations to tackle this. You know, legitimately approaches that can simplify your life. Some of the moments about c equals 0. Well, this force actually passes directly through c. This force passes directly through c. So in fact, you only have ay times 1.5, and you only have 4 times 1.5, being this distance over to here and this distance over to here. So it just tells you what that ay is going to be offset completely by that 4 kilogram load. Okay, your next thing you could do is you could recognize this. Okay, you could sum your moments about point. Okay, that would be point A, which would be the point right here. Now, this sounds weird. Just a thought process. That would be, remember, I can remove or move a force along the line of its action to the point that I line that up. Now, there's one thing I don't like that I'm going to try to fix here. Here, I'll try to fix it up here. Fix it right there. Okay, so I was using red. I think I was using maybe that red. Yeah. So here, I don't like that. Okay. So now, so in other words, I can move this force here. As long as it's along its line of action, I can move it here. I can move it anywhere. I'm just going to move it to right there. Now, interestingly, if I sum moments about A then, now this will be interesting. Sum moments about A at that point, then none of these supply a moment about A, and this one supplies no moment about A because it goes directly through A here. So all I get is this one that is that far apart, which would be d over square root of 2, 1.5. And I get the other one, which is 3 over 4 times 3 over. Okay, that's if I move the load. So this is if I move the load to there. Let's see what happens if I decided not to move the load. If I decided not to move the load and left it here, what do I get now? I get sum of the moments about A equaling to. Now, what's interesting is this one passes directly through A, whereas last time the other one did. But this one does not. In fact, since this is 45 degrees, this distance is 1.5 as well. So, guess what I get? I get d over square root of 2, that's coming from this one to here, times the moment arm from here to here, which that is 1.5. And I still have that minus 4 in the 3. Same equation. A little bit different thought process, but same equation. Okay, so from this one, I should be able to solve that. From this one, I should be able to solve that. The only thing I have left is to solve for the AX. Now, this is an interesting problem because I can actually sum the moments about point D down here, that spot right there. And what's interesting is, and all these are supposed to be equal 0. What's interesting is AY passes directly through this D, so it doesn't produce a moment. But this AX is 1.5 AX, and it's producing an opposite moment to this 4 kilonewtons operating 3 meters away. And so, in fact, I never had to sum the forces in the X or the Y, but at this particular point, I can use those as a check for my answers that I get out of this. So, in fact, I can do some of the moments about C, the moments about A, and the moment about D, and that's my 3 individual equations. These other 2 are not independent. What you'll find is that these are essentially a form of these other 2 equations. And you can think about that like this. If I did sum of the forces in the X equals 0 and just did some random distance, then this would be nothing more than a sum of the moment about something. So in fact, the sum of the forces and the sum of the moments equation can be thought of as the same thing. However, some people may choose to work this problem here and get the AY and then start doing some of the forces in the X direction and then some of the forces in the Y direction, and set those equal to 0. So in other words, this force, that force, and that force should sum together to give you 0. Also, this force, along with that force, should sum together to give you 0. So that being the case, you would immediately recognize that this force has to go back to the left, but you don't have to figure that out quite yet. So, that being the case, I should have been a little bit more rigorous here about a couple things. One, and let me just go back and fill that in so that we see I just wasn't. So when I sum the moments about C, this spot right here, I did AY times 1.5. So that showed me that that was going to be positive. Okay, now what's interesting here is if you look at what I've got, I have a problem here. Let me show you what my problem is. If I assume that to be positive, then this is going positive, and this is going positive, which will tell you one thing, and that is the sign of that is probably going to flip. So in fact, this should have been a positive as well as the other. Now, let's look at A. Is at some moments about that point, first thing I did, the initial one, the first one, this one, I had done this. I had copied this and slid it along its line of action there. If I did that, and I'm summing the moments about A, and then I believe what you're looking at is this is going to be my positive. Now, here I had that dy, and it was going this direction. Now I have this one going around C that direction, so it becomes a minus, and we're okay here. Now, on this one, I was basically leaving the force here, and I was essentially summing that force. Well, this time, it's the dx, not the dy. So before it was the dy going this way. Now it's the dx going this way. That being the case, this force goes that way. That being positive. And then I get this 4 going this way, the other direction being negative. Then I came down here and I did the moment about D. Okay, and I chose AX to be going this way as being positive. So I chose that as being positive. And then guess what? That is also positive. So you have to be a little bit more rigorous than what I was there. So the first thing you do is you set out your forces, and then you pick what's positive on each of these moments and make sure you hold yourself to that rule and don't do like what I was doing a minute ago. Okay. So I'm going to come back to this one last. I don't like it, but it's okay. So in this one, this one has interesting, what I'm going to do, try to do the best I can. Oh boy, that didn't quite work right. Well, anyway, that's not exactly what I wanted to have happen, but we're just going to go with it. Okay. Okay, so there's my beam. Done a not so good job here. So I'm going to take, the first thing I'm going to do is take these 2 triangular loads and put 2 single loads that are one here and one here. They're actually the same level. Since they're 3, they're 1 and 1, 1/3 from the heavy end. So what I'm doing, what I'm saying is I'm staring at this one and I'm figuring it out. It is going to be 2 from this end, 1 from this center section, and this is going to be the same thing. What's its value? What's the area here? W times 3.5. So 3W over 2, 3W over 2. And that's going to be the equivalent of taking your distributed load and replacing it with the equivalent point load. That's step 1. The next step is to recognize that the force simply goes perpendicular to this wall here. So it's going up like this. Now, that being the case, this is going to be 3, and this is going to be 4, and that's going to be 5. That'll give you your direction there. Over here, you don't have, okay, so let me give you that. 3, 4, 3, 4, 5. This one, you're just going to have a bx and a by. And now, you just got to go through this process. I'm going to assume from this picture that these are almost elevated at the same point, because he didn't tell me they weren't, which means this is point A. If, and let me be more rigorous this time, if I sum the moments about point A equals 0, I'm going to choose that to be positive. Then the first thing is this force is making a moment that way, which is a negative moment. Its value is 3W over 2. Its moment arm is 2. Now, this force is creating a moment in the negative direction as well. Its value of that force is that its distance is 1, 2, 3, 4. And then finally, this one will produce no moment about A, so that's gone. This one, however, will produce a moment going that way. So that's going to be a plus by times 3, and then another 3 gives me 6. So that's how you find, that's how you'll find the by. Variety of ways you could find the other one, but I could go in and sum the moments about B. And if I did that, I would have the W now going this way about B, which would be 3W over 2. The moment arm here is 2. And then this one would be producing a similar thing, 3W over 2. This time it would be 4, 2, 3, 4 over. Now, what I would get here is this force would be broken down to a component going north and one going to the right. I'm only interested in the one going up, which would be going in the minus direction, which would be A, the force A, which I don't guess I really ever said it, but I'll just say that that's going to be the force A times, in this case, 4/5, because that's the one going north. Moment arm is the total distance over there, or 6. So from this one, you get the by. From this one, you get the A. Now you could turn around and sum the forces in the, let's see, which one? The X direction. Give me 0, so you get the bx, which would not be known. We'll assume that direction being positive. And then you would say, well, the only other component is the A component going to the right there, which would be 3/5 of A. And it's going to the right, so it's positive. And so in that one, given that you would solve this, you'd solve that next. And that's pretty much it. Now the dreaded one we don't like, the one that's very annoying, the one that I don't like, and for obvious reasons, we talked about last time, but I'm going to accept this, and I'm not going to like it, but it's okay, because if I were working this in a non-academic setting, I would definitely include those moments, but I am not going to now. So this can have the bearing can have a supporting load going up. It cannot have one going down this way, or can it? You know, this is a question, because we talked about the tapered bearings, and the tapered bearing can resist a force going down this. But this one says it can't. Okay, so this is a very nebulous area. What I mean by that is, when we talked about this a minute ago, where did it go? Oh, it's gone. I had the bearing on the page, I had everything there, and the bearing is gone. So, oh, here it is. So the other thing, some guy just walks out to your car and just pulls it, your tire and your whole assembly comes straight out. Not going to happen. So in fact, this thing is going to resist a pull or a push. It's going to resist a torque. It's going to resist everything. So in fact, he's showing this, right? And depending on the design of this bearing, which is much more detailed than what he's showing, he's saying you can just pull this shaft and it'll start moving. Okay. He's also saying in his examples that if you just torque this thing this way, like so, it's just going to start moving. When in fact, he's showing this, that it'll have a resistive torque, resistive moment to that. Now, the only one that I think is a given is that this torque right here going in this direction is going to be free. In other words, you start turning the shaft, it's just not going to resist you. And so you don't have a moment like that. The rest is all open territory. But we're going to follow his little thing in which he says, okay, it can't do that. Do I believe it? No. Okay, so here's the other thing. We'll say, here, I'll put it over here. CY. He's saying it's not going to have a CX. He's also saying it's not going to have a moment X. This is the one that I would agree with. He's also going to say in this example that you're not going to have a moment about the Y, meaning you're not going to twist this way. And you're not going to twist this way. So in this particular case, for this problem, this is all you're doing, is you're putting a CZ and a CY, a BZ, hang on, BZ, and this time a BX. And then over here, you're going to put, and I'm trying to draw them in the positive direction, a Y and an A Z. How many unknowns do you have? In this particular case, you've got 6. How many equations do you have? You actually have sum of the forces x, sum of the forces y, sum of the forces in the z, sum of the moments about x, sum of the moments about y, sum of the moments about z. So you're going to have actually 6 equations. So this is a solvable problem. How you decide to solve it, kind of up to you. He's got an f here, and more than likely he tells you what this f is. Let me look at the problem. See if I still have it up here. Anywhere. Don't, but here, hang on. Let me look at the other screen. Let me see what he tells you. Is he telling you what f actually is? Hang on. Computer is slow. Okay. Computer is very slow. Okay. In fact, yeah, he does tell you that your value of f is some number. Okay. Then what he's doing, he's kind of, let's see, how do I get this to the main screen? It jumped. So he's telling you, he's asking you, what is AY and AZ? AY and AZ, these two right up here. Then he's asking you, what is BX, BZ, which is BX, BZ, the two in the middle. And then he's asking you, what is CY, CZ? CY, CZ. He's asking you these three. So he's asking you each of these in a chunk, you know. Unfortunately, there's not much you can do except just doing these. So you're going to have to solve them all together. So if you have this value, for example, let's say we sum the forces in the z direction. What we're going to get is the z, let's see. And we'll say we're going to take this as a positive coordinate, just like the coordinate right here. You're going to see AZ plus BZ plus CZ minus F. But there's still going to be 3 unknowns. So then the next thing you're going to have to do is sum the forces, I guess, in the x. It really doesn't matter. We're going to pick it in the coordinate direction there. X is, you're just going to say BX. Okay. And then, hang on, sum of the forces. I did the X, now do the Y. So I get AY plus CY. Okay, so I got a AY and a CY. Let's see, I don't have anything but an X, so, alright, so I've got that. The next thing I can do is, I don't know, sum the moments about A. It really doesn't matter. It's a vector equation. So, how do you determine that? Well, here's the way I'll do it. I'm just going to do the A and let you do all the rest. Here's the deal. Sum the moments about A. I'll say R to, I don't have to do it to A because a vector to A and these, they pretty much cancel out. So I'm going to say draw R vector, cross it with the force at B, plus on R vector to the force there, crossed with the force. Okay, that force right here. and then plus the r vector to C crossed with the force at C. So if you look at each one of these, you'll find something interesting. Let me see if I can do each of these here. I'll say this is equal to I, J, K. Let's draw the vector to B from A. So I'm drawing this vector right here. That would go out 0.6 out this direction, and then it would go 0.6 out the Y, and nothing out the J. Then my forces that I've listed at B are simply those two. Bx and B, oops, sorry, nothing, and then BZ. So this one would be that. Then this one would be something slightly different. It would be I, J, K. The vector that goes from here out to the point of the application of that load is in fact 0.6, 1.2, and 0. So here's your 1.2, there's your 0.6, and the force here is simply going down in Z. And then your final set would be this, R2 actual all the way out there to C. It's going to be I, J, K. The R all the way out there to C is going to be, ooh, okay, almost goofed, but that's a, that. So this is a 1, 1.2, okay, and then nothing. And then you get nothing, you get a CY and a CZ. Okay, so when you cross all three of these, if I did these right, you add this one to this one to this one, and it's got to equal to nothing, nothing, and nothing. That will give you three equations. So you can use those three equations to solve for your three components. And so that should be enough information there to solve for those. And so with that, I think we may have gone our whole hour. Let me check. I don't know. Hang on, let me go look. There is some timing. Whoops. Okay, hang on. Hang on, hang on. Oh, is that it? Okay, wait a minute. How do you tell? Whoa, that's weird. Oh, well, technically we have done our hour. I started a few minutes early. Let's see. So I'm going to call it quits there.